All right. Hello, guys. My name is Lazaro. Thank you all for coming. We're going to be going over a problem that Giri gave us yesterday, specifically sword counting. Giri didn't really finish it because there was a little bug that we were left off on. But we're going to try to discuss it and hopefully come to a solution and see if we can figure out ourselves. First, I'm just going to bring up the problem right here for the live stream, in case anyone here doesn't know it or doesn't remember. Does anyone want to summarize it in like 1 or 2 sentences? Okay, so we're given this structure, or this graph right here, that's called a sword because how it is structured. And our goal is, given a graph, which could potentially have up to 100,000 nodes and 100,000 edges, how many of these swords are found in that graph? No, I think that was like 2.
Okay, that was 2 sentences.
Yeah, I think it was 2. So it's as simple as that. That is the main goal. Find how many of these structures are in a graph given to us. You can look at the input. You guys can draw it out and make sense of it. And then something else, in case we really cannot figure out at all today, we can look at the solution. Because there is solutions online by ICPC, and they sent it out, or not sent it out, but they just have it posted. And it's right here. We can look at this later on, but for now, let's see if we can come up with our own idea to solving this. So I'm just going to disconnect all of this right here. Take the computer elsewhere. Look how fast this was.
Do you know how to recommend like a difficulty level?
A V-Judge?
Yes.
Yeah, I think these are like difficult levels like 8.
No, I mean like this one.
Oh, no, go to Caddis. Caddis is where they have it.
Oh, okay.
Okay, so change this. All right, cool. All right, so there we go. Let's point it right here. Then let me also put all this up and turn the lights on. All right, so I'm going to draw out an example. I'm going to ask you guys what would be the answer to it. Okay. So let's write out an example. Okay, so how many swords do we have for this example right here? You're off by 4, you're off by 1. So 1, 2, 3, 4, 5, and then 6. Right? We all agree on that? Okay, cool. Awesome. So we have 6 for this example, and then like I just said, if I were to name them or give them labels, You don't name a graph, you label a graph. One sword can be 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 7, 1, 2, 3, 4, 5, 8. Then since this is symmetric across the x-axis, just flip that, and you have another 3, which will give you 6. So now let me ask you guys another question. How many swords do we have here? David, this is also for you. Try to redeem yourself.
How many swords?
How many swords? Okay, Demba says 0. You agree? Do you agree because you actually agree, or do you agree because you gave up?
I agree because I tried to count them.
Okay, it's exactly that. So if we were to make this node right here, which is the only node we can make the middle, so let's call that M. And remember in our sword structure, one of the nodes had to have at least 4 neighbors. And that node that had 4 neighbors, we're going to call the middle. So if this node is the middle, then we can say this is part of its sides, these 3 right here. That means there's only one remaining node that could be considered the blade or these 2 top. If this is considered the blade, then we're missing one more, and we don't have any valid option for that because the other node was already used. Therefore, we can't really construct we can't construct a sword out of this graph. Let me now just augment this a tiny bit, and let's see what David says about this graph.
I see one, but
There's just one. What does Demba say?
I think there's 2.
Okay, he thinks there's 2. You want to come up and draw it?
You can just draw it.
Here, let me make it easy for you.
I can see 2.
Where is your 2?
There's one that could go to. Let's say you start from 6, right? The sides of the handle could be 3, 4, and 3, 4, and 5, and you can have 2 as a blade and then 1 as the tip. Another way you can do it is you can have 2.
It's 1.
Oh,
Yeah, it's 1. Yeah, now he has some redeeming to do. But yeah, David, you said absolutely correct. It is 1. The only way for there to have been 2 is if I did something either like this, or I gave a node to this one. That's how we can have 2. So now, how can we really determine this? Like, what calculation are we doing? I should probably draw out a better graph, a graph that is valid. But I know we talked about some calculation last class, if anyone remembered, or last lecture. Does anyone remember what it was, or what was the math behind solving this question, or at least some variant of this question?
Let's say all the vertices that have a degree of 4, right?
Mm-hmm.
Then from there, choose check if there's an adjacent neighbor with a degree of 2, and if there is, then go to every single one of the adjacent neighbors that have at least a degree of 2, right? And then check the number of adjacent neighbors those are, and choose 2 times the degree minus 1.
Okay, so yeah, you said it perfectly. If we recall the structure of a sword graph, it is like this, and we know there's something unique about this structure, and that is that the middle node must have 4 neighbors. So what Dembo just said is try to find those nodes first, look at the nodes that have 4 neighbors, and then look at a a neighbor of that node and verify that it has at least 2 neighbors. That's one big thing is at least, because it might have more than 4 and we still want to consider it. So in this case, which node would we first look at? Let me once again label them. David, which node will we consider looking at first for this graph right here?
I'm going to pick
3. All right. Demba, what do you say?
It could be either 3 or 6.
OK, so it could be 3 or 6. You guys are absolutely correct. Do you see why it could be 6, David?
Yeah, I do.
Yeah, cool. Because both 3 and 6 have 4 neighbors.
Yeah.
So let's put that into a set. Let's call it U. Let's have 3 and 6. Now what? With this information, what do we have to determine next?
Check all the neighbors of 3 and 6 that have degrees of 2, at least 2.
You agree with that? Cool. Check all the neighbors of 3 and 6 and find one that has a minimum degree of 2, which will be verifying or checking for this section of the sword graph. So what we're trying to find is, let's call that B. It's equal to hey.
And then you know.
Call this capital U. All right, cool. So let's call it a set B. Let's make that equal to neighbor of U if and only if the degree of that U has at least 2. Right. That notation makes sense, right? Yeah, it makes sense. All right, cool. Let me just simplify it, and this is going to essentially be equal to what? Give me half, Demba, and I'll ask you guys for the other half.
2 could work. 5. I mean, which node are we considering? 3?
Any of them.
Okay, considering 3.
Like, you know what? Let's do a dictionary. Let's do it as a dictionary or a hash map.
Okay, so you can use 2, 6, or 5.
We can use for 3, 2, 6, or 5. Yep, that's right. Now for 6, which nodes can we use if you know? If not, it's fine. Okay, yeah, that's fine. David, how about you? If 6 is our middle node, which node can we use to construct this section of the sword graph?
We could use 3. We use 5.
Perfect. So we can use 3 or 5. All right. And why can we use 3 or 5? Because if we look at the structure of a sword graph, there's one node that has at least 4 neighbors. We stated that, I guess, here, which is 3 and 6. Either 3 or 6 can be used as this middle node for the sword graph. And now we want to construct this second part where we want a neighbor of the middle that has at least 2 neighbors. So if this is our middle, then a node that has at least 2 neighbors would be 2 and 5 and 6, if that was our middle. If 6 is our middle, then the neighbors of 6 that have a degree of 2 or more will be 5 or 3. All right, so now with this information, what do we want to do? If anyone remembers.
Now with this information, we also want to do the same thing we did for but this time for the nodes inside the sets of the 3 and 6.
And okay, so now we want to, let's just say, okay, so something like that. And what do we want to do for each and every single one of these nodes?
We want to check if they have, well, we don't really even care. We just need to count. Well, we need to count how many nodes they have adjacent to them.
So now you're saying something like that.
You know, hold on, let me think about it for a little bit. Okay, so what we need to do now is for 3 and 6 again, we need to count how many nodes they have. Okay, we could start with the, okay, so for both 3 and 6, we need to count how many nodes they have adjacent to them. That are not like B, right? And we also need to count how many nodes we have inside of every like 2, 6, 5 as well. How many adjacent nodes they have, which will give us the number of tips we can form.
And how much would that be?
In this case, you want to count the 1 for 2 would just be 1. The 1 for 5 would be 1 as well. The 1 for 6 would be 1, 2, 3 would be 3, excluding the 2, right?
Yeah. So
something like that.
Yeah. So for every single node, like first we're going to be selecting this as a middle. For every single middle, which is this part in the sword graph or in the sword structure, one of them must have a path length of 2. So the number of neighbors now gets reduced to 3. But that's if it exactly has 4. It could have more. So we want to say the number of neighbors of M, in this case, minus 1, choose 3. That's how many different combinations we can form with these handles. And then the blade, the degree of the blade, which is this path, this one right here, minus 1 would tell us how many neighbors we can choose to construct the tip without choosing the edge that goes back to the middle. That part made sense? Any questions at all? As you can see, this is a hard problem. That's why not many people are here. They decided to skip it and or too afraid. But if you guys have questions, go ahead and ask me.
It makes sense now until we get to the triangle.
Yeah, let's say it one step at a time. So I'm just going to do that right there. So something like this, do you guys agree with this computation? For every single middle node we're going to choose, let's look at all the nodes we can choose to be part of the blade. And then the degree of the middle, minus 1. Let's choose 3 from those to see how many combinations we can get for these handles. And then multiply that by the degree of the blade, minus 1, which would tell us how many tips we can construct. And of course, to make our lives a little bit easier, maybe make the time complexity better, we can move a couple of things outside. Instead of repeatedly computing it. Oh wait, could we? I don't think we could actually. No, yeah, we could. I think we could. Right? That's logical in math, right? Since these two are being multiplied, but I can bring that one out because this is constant. Yeah, that makes sense.
I mean, wouldn't it still be the same thing? Because
Yeah, it's still the exact same thing. It's just that instead of doing this computation multiple times, I'm just going to do it in the outside. It's a little bit faster.
Yeah, yeah. Okay. I mean, like, I don't see how. I mean, I guess it depends on the implementation. Like this makes sense. Like if you break it down, it's still the same formula, right? You can always take
Yeah.
it out of this.
The difference, if you want to look at it in ways, the difference is this, right? We're doing factorial of n for every I and then for every j. We can see how this might be bad, of course, because factorial is pretty expensive. But although we're doing something similar, a better approach will be this. There's no need to put it inside of that other for loop, right? Because here you might get n cubed, here you have n squared. So this approach is better. So that's why I'm doing that here. That's why I moved it outside. And I know the camera can look at it, but there we go. That's our logic, an example of how this can save us a good amount of time. Cool. But now, is this going to be the answer we're done? Is that all that we need to do for this scenario or for this problem? Huh, David?
No.
The answer is no. Why, David?
Caught me on that.
It's because we have something that starts with a T, right? It's a special shape. What shape starts with a T? Only has 3 sides. There we go, triangle, yeah. It's because we have triangles. As you can see right here, we have a triangle, so there are some swords that are invalid. Which swords are those, David?
So we could say it's 6, right, with the 5, 7, 8, but then goes to 3, but then the 3 goes to 5. So
Exactly.
are the hilts.
Perfect. So that's actually good that you said that. You said hilt. Let's set some vocabulary.
I might have the wrong vocabulary.
No, your vocabulary is right.
Okay.
We can call it the hilt.
Hilt, handle.
This could be the handle, this the hilt, but it's fine. Let's just call all 3 of those hilts. Let's call this hilt, hilt, and hilt. Let's call this one the middle. Let's call this the blade. And let's call that the tip. Just so we have some foundation for vocabulary. David is saying that if we choose 6 as our middle, and then if we choose 5, 8, and 7 as our hilt, we cannot construct a sword that has a blade 3 and a tip 5. Why? Does anyone want to tell me? All right, you got this. All you.
It wouldn't be straight, right?
Huh?
It wouldn't be straight.
It will have to go up straight. It cannot go back to 5 because 5 was already used. So we can't allow it to go back to 5, and we need to tell it to either go to 2 or go to 4.
Yeah, the tip of the blade was welded into the hilt. So
Exactly.
straight.
So it can go either to 2 or 4. It doesn't really matter. It can go straight up or to the left or the right, but it cannot go back to a node that was used as a hilt. So this answer would be correct if we're operating on a graph that is a tree. Does anyone know why it would be correct if the graph was a tree?
No cycles.
Exactly, no cycles. A tree doesn't have any cycles, therefore we won't have any of these triangles, and we won't have any bigger triangles, which really won't matter. It wouldn't even be called a triangle if that was the case. So how can we circumvent this?
You know, like how you're doing n choose 3,
Yeah.
right? To find like how many combinations you can get by choosing like any random combination. You can also like maybe do another n choose the number of like triangles you have or something similar to that. That that's going to give you how many invalid ones you're counting and then subtract it from the overall.
Yeah, so that's exactly it. We want to, once we see a triangle, in this case will be nodes 6, 5, 8, or 6, 6, 5, 3, or 6, 3, 5. If we see a triangle, let's compute how many swords can we construct with this triangle. That count of swords will be called our invalid swords, and then subtract it from our total. So how can we do that? Let's look at all the B's. So let's do this here. I'm going to do it separately, but let's take into account that there might happen at the same time. If a neighbor of B, if a neighbor of B is equal to a neighbor of M, or sorry, a neighbor of U, I should say. Let's now compute the number of invalid triangles we can construct. We just verified that there's a triangle. Why? Well, let's recall that U, let's make U our 3. That's our middle. Let's make B our 5. So if a neighbor of B, what are the neighbors of B? Anyone? Give me one. 6, right? George, give me another.
6.
Another that's not 6?
3.
3, exactly. If a neighbor of B, which is 6 or 3, sorry, 6 and 3, is equal to a neighbor of U, David, give me all the neighbors of U.
2,
All of them.
4, 6,
One more.
5.
5, okay. All right. So if a neighbor of U is equal to a neighbor of B, in this case, this is going to return true because the neighbor of B is 6, and a neighbor of U is also 6. So another way of saying that is if the intersection between neighbors of both U and B does not equal a null set, then we need to do some logic. What logic do we want to do? This is union. Thank you guys for calling me out. That's intersection, right? We almost let that one slip. So now we want to figure out how many of these swords can we form with this triangle. So we're saying that we're going to restrict, or we're going to set in place that we chose this edge. Crap, that's actually not the correct one, because we're doing it from 3 and not 6. Okay. We're going to say that we chose this edge as our blade. And we also chose this one as our hilt, which is the tip. So whatever this intersection is, let's say it's 6. Keep in mind this intersection could have more than just one element, but we could consider one at a time. So in this case, the intersection would be 6. And now we want to ask ourselves two things. If we are for sure choosing B as our blade, and we're choosing 6 as our hilt, so these two are stuck together, let's now move them. How many of these swords can we construct? The answer is pretty simple, because if we already chose this node as the hilt, we want to ask ourselves, now how many ways can we choose 2 more nodes to complete the hilt? So that calculation for that is going to be the degree of U minus 2 choose 2.
2 because of the blade and the invalid.
Exactly. 2 because of the edge to the blade, and 2 because of the edge to the hilt that's also going to be used as a tip. This is how many invalid swords we could construct with just taking this edge and then taking this edge as well. But like I said, the size or the cardinality, if we're talking about just sets, of the neighbors of B intersection the neighbors of U could be greater than or equal to 1. Of course, I'm saying greater than or equal to 1 because we are saying that it does not equal no set. So there could be multiple of these nodes. How can that be? Well, let's say 5 has an edge to 2. That's another triangle that we create, which is 5, 3, and 2. So for every single one of these elements, let's go over it and let's do this computation. Another way of doing it is just finding those invalid edges. Counting how many of these edges are invalid. At the end, do this calculation and multiply it by those invalid edges.
Wait, so that's neighbors of B intersect the neighbors of U is not equal to 0, and then you subtract that 2. That gives you like the combination of tips you can make from B.
Yeah. How many swords you can make using B as your blade and 6 as your tip.
But it gives you like the actual like valid swords that you can make.
No, it gives you the invalid swords you can make.
Okay, because you're using the ones that, okay.
Yeah. So now, David, why is this? What type of edge is this called? If you don't know, it's fine. It's like it's just like a
It doesn't divide
Yeah.
it into 2 separate.
no.
That has to do with the. It's not a critical edge. It doesn't divide into.
Starts with a B. BA. No, back edge. It's a back edge because we're saying that if we ever explored this node and we're looking at 5 and we try to go from 5 to 2, this is going to be an edge to an already explored node. So this edge is called a back edge. That's why I told you like it doesn't really matter if you don't know. It's like a trivial. It's like one of those like vocabulary quiz questions. I don't know. But yeah, I just wanted to get your attention.
Thank you.
I didn't mean to call you out.
You can do it. It's all right.
All right. So yeah, so let's count the number of back edges. So instead of doing this for every single invalid node, let's just count the number of back edges, right? And then do this times, I am dyslexic, I'm sorry. Times the back edge count. And that way, that's if we store this in some answer, let's say invalid plus equal that. At the end, once we come out with this, if we say that our answer is equal to this, then at the end, all we have to do is answer minus equal invalid, and we have the correct amount of swords. Or something like that, at least.
So all the 100 of the invalid swords are done with the triangle, right? So with the blade edge. That's when you calculate, use the number of invalid edges and check the combination of
Yeah.
tips that you can make.
Because we have to know which edges are invalid, to know if an edge itself is invalid, we have to look at the blade and look at the neighbors of the blade and see if it takes you to one of the neighbors of your middle.
You know, but depending on which one of these edges you use, right? I guess it doesn't matter because the other one is gonna count in the subtraction. Okay. But what I was thinking is like you might be like the formula you have there for the neighbors of B intersect the neighbors of U. if you multiply it by the back edge,
No,
you might have
times.
times the
Okay.
back edges, you might have like a huge value, which then if you subtract from the answers,
Uh,
it will give you lesser edges.
I'll tell you right now how big. So, okay, I see what you mean.
Because let's
Did I not have a green marker? Yeah, I did. Completely forgot I put it in my pocket.
let's say like
There we go. I think that fixes what you were talking about.
no, like, let's say now you have a thing, a back edge from 5 to 1.
Okay.
Yes, if you have a back edge from 5
It wouldn't be a back edge. It'll be a regular edge, because it's not going to a neighbor of 3, and it's not going to a neighbor of a node that could be chosen as the middle. So that's a valid choice.
So the definition of back edge is like slightly modified to just be if it goes back to a neighbor.
To only to a neighbor of you. Yes.
Then it makes sense.
Yeah. Right. So. This is also totally feasible, so we don't have to really worry about big numbers, because we're saying that in one of the constraints, it is that the number of nodes is less than or equal to 100,000, and the number of edges is less than or equal to 100,000 as well. So if we have a fully connected graph, how many neighbors can a single node have? Yeah, but let's say the edges are spread out evenly, right?
Edges are spread out evenly.
Because of course, if we want to construct, if we actually want to find some sort of sword, let's just say that evenly as possible, how many edges would every node have? You guys remember this already, right? I can remove this. You guys know how the structure looks like? Yeah. Okay. David, yes. Yeah. So there's a calculation you can do, and thank you, Ricky, for teaching me. I don't know if you're watching, but if you are, thanks. Thanks. All right, cool. So it's going to be n times n minus 1 over 2. That's how many edges you can have for a set amount of nodes. And since we know this is going to equal a maximum of 100,000, then that's going to be equal to n squared minus n minus 200,000. So now, how can we solve something like this? Does anyone want to tell me? What type of polynomial, I guess, is this? Quadratic. So we can use the.
You can like solve it differently. You can partition it like into, like, I don't remember, but like
Quadratic formula. The answer is
use the quadratic
yeah.
formula. You can also like not use the quadratic formula and partition it. Like you can
Okay.
find a number that I don't know. I don't remember exactly. I've forgotten this stuff.
Okay,
You
all
can
right.
also use the quadratic formula.
So yeah, it's quadratic formula. I think the answer is, and it's around something 450, unless David is searching it up right now. Okay, he's not. So it's fine. You don't have to do it. It's okay. So I think it's around 450. So with 100,000 edges, you will have around 450 nodes that you have to have in the graph. What does that mean? How does this help us in any way?
What's the number of edges you can have in the graph? It's
The
like 450.
number of nodes.
The number of nodes.
So that tells us one thing. Number one, let's say since it's fully connected, they're all going to be middles. They all have at least 4, right? Or guess we can just assume that. So that means our time complexity is going to be O of n for doing this part, and then O of n for doing this part, and then outside of it, it's be O of n cubed for this part.
Wait, can you go over that again?
Yeah, which part?
Like just how you got to the whole thing.
So here we can go over O of n, because we're just summing over all the middles. And then here, we can also do the same thing, because these will be all the blades. And since every other node is connected to the middle, the number of blades could be around 450 as well. And then this part here, you could do this separately outside those two for loops. But this is going to be of n cubed, because you have to iterate over u to find a u, then iterate over b to find a b. And then to see if there's any intersection between them, you might have to do another of n. So that's we of n cubed, which is possible with 450, right? Not an issue at all. But of course, that's not going to be the case. It might be somewhat much worse. We can say that our u, the cardinality or the size of u, could be actually close to 100,000. Let's leave it 100,000. I think it's for sure going to be less than 100,000. It's for sure going to be less than 100,000, because if you're saying that the number of nodes that can be chosen as middle is 100,000, then that means every node needs to have 4 edges, and 100,000 times 4 is going to be more than the amount of edges they will give you. So let's just say something. Let's just say 80. Screw it. All right. Let's say 80,000. Now our second for loop, which could be b, might also be something pretty large, around this size. Let's say somewhat close to this size. So that's going to be 8 times 10 to the 4th, 8 times 10 to the 8th. Or 16 times 8 to the... No, oh my god, I'm being an idiot. It's 8 times 10 to the 4th squared. Right? So that's going to be 64 times 10 to the 16. No, sorry, 10 to the 8. There we go. That part makes sense. I think this is right. Because you just bring it down. Now it's 8 squared times 10 squared. 10 to the 4th squared. 10 to the 4th squared is 10 to the 4 times 2. 4 times 2 is 8. 8 squared is 64. So
what does that number give?
that gives us roughly our time complexity. So we're already at 6 billion with just this. So it's not going to be the best. And I think our time limit is 7 seconds or something like that. So this is pretty bad.
Wait,
Right? Did I do it wrong?
6 billion nanoseconds?
No, I'm saying like how many iterations were due.
Oh.
Yeah, it's something like that. Of course,
More than that.
you might be a little bit less. 80,000 is pretty extreme. But I'm going to erase this because I'm not totally sure if that's right. But for a fully connected graph, we would be okay. So obviously, although this might give us an answer, it's not really a feasible answer in solving it. So now the question is, what is the correct answer? What do we have to do? Does anyone know?
What we have to do to reduce the time complexity?
Yeah, what do we have to do to actually solve this?
Actually solve this.
known.
One thing you can do, like, one thing you can do to at least reduce this time complexity would be to like you see where you're checking for like this is a B and then this is a B.
Mm-hmm.
I don't think you need to like you can do it in less than n squared because you've already like in the map over there you already have like B and all its neighbors and then 6 and all its neighbors, right?
Yeah, the degree of B's will be constant.
Hmm?
The degree of B's will be constant.
What do you mean by like degrees of B's?
Like you're pointing out this part?
No, I'm pointing out. I'm saying like the if statement over there. You know,
Oh, yes.
You calculated n cubed
Mm-hmm.
to check like.
But how can we do the intersection of that in less than O of n?
In less than O of n, you can like store them into in less than O of n. You can bitwise add them.
Bitwise add them?
No, you can if you OR them, right? You're gonna get. Okay, if you AND them, if you AND them, you're gonna get everything that intersects.
Yes, I know. But that's will be an array, right? Where the size of the arrays will be the neighbors. No, the size of the arrays will be the amount of nodes there are.
The amount of nodes there.
Yeah.
It's just the amount of nodes that are connected to them that they are adjacent to, right?
Yeah, but
You're saying it's just the amount of nodes that are connected to that current node, right? The neighbors. So let's say for 5. Here. How many nodes are there? 3, 6, how many? So this would be 8, right? If you say the amount of neighbors, both of these can have a 1 here, but you don't know what this 1 represents. You don't know if this 1 here represents the 8, which this 1 represents, or this 1 could represent the 8, and then this 1 could represent the 7. So you want the full list of nodes. So when you're ANDing, you can look at the exact same location, and you know they're both referencing the exact same node.
Yes.
And that going over this and ANDing each and every single one is still going to be open.
so we're seeing the difficulty of the problem now, right?
Wait, so the whole thing is just figuring out a way to see like the neighbors of B and the neighbors of B like intersect, right?
Yeah.
In an efficient way, without it being like O of n.
Exactly.
Because we know for sure that calculating the valid edges is going to be correct.
So now let's look at the solution. Or not really the solution, or
More like what they recommend us to do.
So you know in your loop, if you're at 3, right? If you're processing node 3, right? Like create a set, right? And then put like all the nodes that are adjacent to that 3, right? Which is the handle. And then when you go to B, check like if, like for instance, when you go to B, check the nodes that are adjacent to B, like you're considering to be a tip, and then cross reference everything for 7 created to 3. If it is in there, then
Still be open.
intersect. That would be
It's going to be less than open. It will be all degree of U or degree of P, whichever is greater.
well, it doesn't have to be because like at 3, right? You can put 2, 4, and 5 into a set, right?
And 6.
Yeah, and 6. And when you're at 5, you can just check if there was there. And then when you were putting them in, you could have done that when you were counting it or something.
Okay,
some
okay.
Sort of a map.
So you're still saying now, when you have the 2, 5, 6, and 4 in a set, now we're looking at 5. Go look at its neighbor and potentially remove from 3. How is that still not
But what
open?
do you mean potentially remove from 3?
like remove from the set of 3 and see how many you were able to remove.
Well, you don't have to remove. You just have to check if it is contained in there.
Okay, so don't remove it, just check if it's in there.
It is hashed, so it doesn't like have to search for it.
Yeah, it doesn't have to search, but it's still going to be of n, or in a better scenario, it's really going to be more of degree of 3. Sorry, of degree of b. Because you still have to look at all the neighbors of 5,
All the neighbors of 5.
and then see if it's within the set of, yeah. Yeah, yeah. So, that's actually pretty good. I think that might be the best we can do. Of course, unless b is a really large degree, which is possible. They say we only have one sword in this graph, but that one sword, the blade is b, and b is connected to 100,000 edges. Might work. I'm not totally sure. I actually haven't tried that.
Yeah, like a better way to do it.
Yeah. So as you can see, we were correct about this formula. Times complexity n plus m. Where is m coming from? Is the edges? Okay. Wait, but they usually write edges as e. No, as the cardinal e like that. Okay, whatever. I guess here they made m edges.
Or maybe.
So yeah, we were correct about this. We actually made it a little bit better because we were able to move this out, something they didn't do, but we did because we are smart. But now it's smart enough to figure this out. Not that smart. But now how to do it with cycles or with triangles. They are saying to find all 3 vertices that forms a triangle, and then do this computation right here.
Wait, find what?
Find 3 vertices that form a triangle, and then do this computation right here. As you can see, they're still doing the -2, choose 2, which is exactly what we did, so that still makes sense. But they're doing that for all three vertices. Does anyone know why?
The degree minus 2, choose 2. Well, it's like 2 combinations of the degree minus 2. As in like, wait, that actually, that kind of seems like it will actually be valid, because if you take out the 2 invalid edges that are connected, like in that triangle, right? The 2 edges adjacent to that that makes it invalid, and then choose 2, which ends up giving you how many you can actually make valid.
But why are they adding all these and then multiplying by 2?
Because all those triangles, all those edges could be connected to other edges that could be used as tips. I'm assuming these are the blades, right?
Close. That was close.
Wait, these are, you're counting the number of degrees of the blades.
No, these are not necessary blades. They're just vertices that form a triangle.
Vertices that form a triangle, which they have to either be a blade or a handle to form a triangle.
Yeah, or the middle. One of them is a blade, one of them is the middle. The other is another. It's a hilt.
Yeah, that's how the triangles are formed.
Yeah. But they're choosing 2 for each and every single one of these vertices because each and every single one of these vertices could potentially be a middle. Let's say it's not a middle, right? If it's not a middle, then we know for sure it has less than 4 degrees, right? So, exactly. So -2, choose 2 would give you 1, and that would be correct because that would just be 1 invalid sword. But we're adding all of them together because we're saying if it's possible for these vertices to be middles, how many combinations can we have for creating the hilt? Now let's multiply that by 2 because it's symmetric. Or not really symmetric, but the path going one way is the exact same thing as the path going the other way. If you have an invalid sword graph right here, we can say that this is your middle. That's one invalid triangle. But it's the exact same thing as starting at the same middle and going the other way. So that's why we multiply by 2. You can kind of flip it at the x equals y or cutting the base where the base is the tip and the blade, or the hilt and the blade. You can flip it, and it's the exact same sword. You can construct the exact same, not the exact same sword, but you can construct a sword with those 3 vertices. You can construct 2 swords with those 3 vertices. So that's why we're multiplying by 2, and that's why we're adding all of them together. So now the question is, what is going to be the time complexity of this algorithm? And this is where it gets a little bit foggy. They're saying they're going to call a vertex U heavy if the degree of U is greater than or equal to the square root of V, or the number of nodes. Otherwise, let's call it a light vertex. So they're just defining some vocabulary right here. And the number of heavy vertices in a graph is big O of the square root of the amount of edges. So if the amount of edges is at most 100,000, what is the square root of 100,000? Yeah, somewhere around 100. It's 300 and something? Okay. I think you're right, David, but let me just. $316. David, you redeemed yourself for the next month. No, I'm kidding. Yeah, thank you, David. So it's going to be around 316. That's how many heavy vertices we can have. Now they're saying for each triangle either contains no light vertex or contains at least one light vertex. Don't ask me. No light vertex. That means that a light vertex is less than square root of V. So less than the square root of 100,000. So less than 316 or 317. We have to round up. In order to detect all triangles with no light vertices, choose any 3 combinations of heavy nodes. So, and then a heavy node is one with a degree of U is greater than or equal to the square root of V. And then in order to detect all triangles with at least one light vertex, fix the light vertex, then iterate over all pairs of its neighbors, which will give you the same time complexity as detecting all triangles with no light vertices. And then the connectivity of 2 vertices can be checked in logarithm time. That is true, because if 2 vertices are connected, we can just look at it in an adjacency list, which has a lookup of log n, which I know sounds weird, but log n, that is in C++. So yeah.
Or you can like just put them in a find that they will almost constant.
What do you mean?
If you put all the vertices in a union find, like the structure of the graph, you can check if 2 things are connected.
By just looking at the parent, right?
But you can just like implement it somewhere and just call like find or connected or something. And
Yeah.
maybe yes or no amortized log 10 times.
Yeah. Wait. Yes or no amortized log n?
But I think you could even implement some sort of path compression.
Yeah.
Even take the log down.
Yeah.
Almost constant.
I think it's almost constant. I thought it was constant. Is it constant?
No, like it's almost constant.
Don't they all look to the parent?
They all look to their parent.
Like when you call find, or you're saying union?
When you call find, it looks to their parent, but like depending on the height, that's what like tells you their time complexity.
Yeah, but the height is all going to be compressed to 1.
Yeah, exactly. When all is compressed to 1, it's still amortized constant time, right? At least from what I learned, that's what it is.
Okay.
Because it's not exactly constant for some reason.
All right, so amortized constant. All right, so yeah, we can probably do this better, as Demba said, with using union find. And by this, I meant this, people in the live stream, this part right here. Cool. And that will give us an overall time complexity of n times square root of n times log of n, which is going to be 100,000 times 316 times log of 100,000. And I know that David knows the answer to this right now.
Oh, wait, yeah, that one.
She's 317 because we have to round up. Sorry about that.
Log base 2.
Yeah. Which will be, yeah, 639,000. What do you mean to the power? Oh, I did to the power? Whoops. Okay, that's much different. 10 million, which will be 10 million operations.
So it's like a lot faster.
Much faster, yeah, much faster.
6 billion versus 10 million?
Yeah. So now let's look at the time that they gave us to solve this problem. Okay. And the time is 5 seconds, so that for sure should be acceptable.
Oh, but it was 6 billion. Well, 10 million iterations is how long is that?
I don't know. I know Ricky told me, but let's just say since they give us 5 seconds, they say it takes 1 second to do 5 million or to do 2 million, something like that.
Yeah, you can find it, like how much it is, depending on the equipment.
All right, it's roughly around 2 million or 5 million. I know we have this that I pinged previously. That's for a 1 second time limit. So I guess once in 1 second, 1 second you could do 100 million. I don't know, something like that. It's doable. That's the thing with this algorithm. But now that this is where I leave it up to you guys. That's be the end of the lecture. Hopefully you guys can implement it with this newfound knowledge.
So instead of like all the thing, all you have to do is choose the 2 times the
Yeah.
degree of every single triangle,
I have every single vertex in a triangle, yeah.
and that's going to give you the number of invalid labels.
Exactly. So good luck implementing this. Hopefully you guys have a better experience than I do, because as you can see right here, I did implement it. This is going through all the middles, where the middles is a vertex if the size of that vertex is equal to 4. Once it passes 4, don't really care. I've already added it. There's no need to add it again. That's where I'm doing the combination of n choose 3 for all of its neighbors.
Is that like a built-in function combination?
No, I had to do it myself. And then I'm looking at all the triangles. And of course, we don't want to repeat triangles, so I added to a set of all the seen triangles or seen pair triples of vertices that form a triangle. And then I do this math for invalid swords. And then once I do that, I use the answer minus invalid swords, but apparently it's not correct. I think it gives me time limit exceeded. So there's something I messed up here. So yeah. And I'm pretty sure the part where I did mess up was that I'm looking at all the nodes. I'm iterating over all the nodes instead of iterating over all the light vertices and then doing one with only a minimum of 1 light vertex. So I think it's these 2 parts that I did not implement. Yeah. So yeah, other than that, thank you guys.